Let's tackle these one at a time. Let's work on exam 1 stuff for a little bit. I think we can tackle these units first. Molality, remember that's lowercase m, and that's moles of the solute, and usually the denominator is solution, but it's solvent. Okay, so it's not solution. Where would you see this possible calculation? This will combo with something else actually, so that's wonderful. Molality, I think the only equation that has it is this boiling point elevation and freezing point depression kind of problem. Okay? So I think that's the only time, unless we just asked you to convert units, say, or determine the molality from something given. Remember, the solute is whatever there's less of. The solvent is usually what there's more of. So the solvent is usually what? Water. Okay, solvent is typically water. Okay, so these kinds of problems have 2 typical things that you'll see. Either one is a plug and chug, where they will ask for either the change in temperature, I, K, or M. Let's go over each of these variables. So plug and chug, that's the easiest kind of calculation for this. Molality is the solute and the solvent. K refers to what? The solvent, which would typically be water. So K refers to the solvent. I refers to the solute. Okay? Remember, it's the number of ions or items in solution. Delta T is a change in temperature referenced on what? The solution, but the initial temperature would be the solvent. So compared to the solvent, when you make the solution, how does the temperature change? Okay? So know those. This is, so for freezing point, because that's what somebody asked me, what would be T initial? Typically would be 0 for freezing point, because that's the freezing point of water. And then they want you to find, say, a delta T, how much does the freezing point change when you add some sort of solute? Okay, that's the easy type. The harder type is when they ask for any of the following. They'll ask for moles, mass, sometimes formula, sometimes molar mass. Okay, those are pretty typical things to ask for. Why that confuses students is none of those are variables in the original equation. Because they're not variables, what we're telling you to do, you should solve for molality. Okay, solve for molality, and then convert to what's asked for. Okay? So, for example, if they wanted moles of the solute, if we asked you for moles of the solute, all you would do is look in the problem, find the kilograms of solvent, and multiply through with the molality. So if you multiply kilograms of solvent by the molality, you'll get moles. If they wanted mass of the solute, all you would do, once you have moles of the solute, what would you do? Multiply by the molar mass to get mass. If they ask you, let's skip one, for the molar mass, what you would typically do is find the moles, the numerator, and they'll typically give you the mass. So you would just go mass over moles. So remember, the units of this is grams per mole. Typically, what you would do again, you get the moles from here, from the top, and the mass, you would get, they would give you that number. If they wanted the formula, that could be kind of the trickiest one. You would find molar mass first. What I did in class was a sulfur complex. And so you would find the molar mass first and divide by the molar mass of the atom in the structure. So for example, what I did in class, there was sulfur in it. So I found the molar mass, it was a big number, and I divided by 32.07, the molar mass of sulfur. And the number I got was a whole number, and it told me how many sulfurs were in there. Okay? So those are typical kinds of questions. Again, and you just look for what they ask for. They either ask for something directly in the formula, or they ask for something random, and you solve for molality first. Everything you did in lab was pretty standard sort of questions. Okay? All right, that's that one. Let's move on. And cool, I get to cross off something I was not intending. Okay, let's do crystal structures. Okay, for this one, I'm going to flip in my reader. This is, I guess, other places. This is in your textbook too, just in different form. Chapter 12. First, I want to direct you to an example here. Okay, this stuff on the top of page 29, or if you have it in a different book somewhere else in your textbook or something, this is stuff you should know. Specifically, you should know column 1. You should know column atoms per unit cell. Okay? Sometimes people call that the empirical formula. You should know the coordination number, and you should know the length. Okay? The volume is just the length cubed. Okay? So it's the previous column cubed. And then you should know the packet lengths. Okay? So really, everything except that fifth column is significant. Whether you derive it, or you just memorize it, what have you, those are the most significant. But then what you're going to do for the density, so crystal structure kind of problems, well, they can be different kinds of questions. One type of question is just to give you, to ask you something. You have a face-centered cubic, how many atoms per unit cell? Or sometimes, I think if you've seen on some of my practice tests, we'll give you a molecule you haven't seen before, like a packing structure you haven't seen, maybe not one of these. And we'll have you calculate the atoms per unit cell. Maybe I'll do a quick review on that. If you need the atoms per unit cell, and it's something you haven't seen before, I'm going to make a little table. Location versus number of atoms. Okay? If you find an atom in the center of the unit cell, how many atoms are in the unit cell? 1, because it's in the middle. If you find one on the edge of one of the sides, the edge of one of the sides, how many atoms are in the unit cell? On the edge, okay, if you don't know what an edge is, just in case, you find something right there. How many atoms are in the unit cell? 1/4. 1/4. Okay. If you find something on the face, the face is right here, the middle. How many atoms are in the unit cell? 1/2. And then if you find something in the corner, 1/8. Yeah. This, I mean, I just derived it each time by visualizing it, but these you should know, and this is what you use to add up anything we would give you that you don't recognize. Okay? Alright. So those otherwise would be based directly on the table, or it could be one of these calculations. Yeah, there's a question.
Yeah, how do you tell the difference between like a center and a face? Because sometimes you're drawn almost the same. Like inside.
A center and a face, just because of the picture looks ugly? And you can't tell?
Yeah, like if you can't tell, like, what's the name?
The face, usually, if you're looking carefully at the picture, if it's on the face, it should be directly centered on a box. So they would be here, or literally right there. If we're intending it to be on the center, then you kind of look at the whole outline of it, and it should be kind of in the middle. So it shouldn't look in the center. So the middle, I would consider it right about there. That would be one that's kind of in the center. It's obviously not in the edge, because the edge would be right here. It's not on a face, because the face would be here. Does that make sense? So it's kind of offset that fits none of these categories. So then I would consider it in the center. If you think it's a really bad copy and you can't read it for some reason, I'd raise my hand and ask it to you. Like, where is this dot supposed to be? Is it on the face or the center or whatever? Yeah, that would be the copier's fault, I guess. Okay? Yeah, no problem. Okay, the other kind of question besides directly saying from the table, Like, what's the coordination number of a face-centered cubic? By the way, what's the coordination number of a face-centered cubic? 12. 12 is always a good guess if you don't know, because several of them are 12 for the coordination number. Okay, for the density, if we ask you something about that, I consider this mostly a conversion problem. So the volume, you would say, is just the length cubed. The length you get directly from the table that I just showed you. If you know it's simple cubic, you know the length automatically. Okay, that's listed in the table. It also should be in the book if you don't have my reader. The mass, you have to do some conversions. Let me write that in a different color. You need to know the atoms per unit cell. What you need to do is convert this to mass, because mass is in units of mass. Hopefully that makes sense. So, atoms per unit cell, first convert to moles, 6.022 times 10 to the 23rd atoms per mole. Okay? And then convert moles to grams. And so that's the molar mass of whatever entity you're working on. Okay? So you just use a conversion like that. Make sure you're in the right units. Usually, we want density in grams per milliliter, or the same thing, grams per centimeter cubed. Okay? Those are the same units. Usually we want it in those. So make sure you put it in the right units, divide mass by volume, you should be set. Okay. Can I move on to the next? Those are the different types of questions you can see. Alright? Next, let's see what we got. We're rolling here. This is awesome. Okay, we did crystal structures. Let's do KP. KP. Let's do this equation. N2 plus 3H2 goes to 2 NH3. Let's assume they're all gases. Okay, all of these are gases. And let's say we gave you a KP. So typically, if it's a real KP problem, then we'll give you a KP in the question, and we'll give you pressures in the units of atmospheres. You need to be in the units of atmospheres, okay? And then we'll go through, and I'll do a little kind of example here in just a second. If we give you pressures in KC, you need to convert one of them to the other. So we give you pressures in KC, either change KC to the KP, or change the pressures to concentration. Okay? But if we give you pressures in KP, there's nothing you need to convert. Just leave it as is. And there's a couple of nuances about this. So let's say we give you KP, and if we ask you for equilibrium partial pressures, that means the ice table. We don't always have to use the word equilibrium. If it just says partial pressures, that's an ice table. So you'd set up I, C, and E, and then let's say it's 0, 0, and 5 atmospheres, for example. Then you would shift towards the 0. Oh, what is this? Actually, what do I put here? Minus 2x plus 3x and plus x. So you have x, 3x, and 5 minus 2x. And you would say, okay, zoom out a little bit. KP is equal to products, and this is partial pressures now, partial pressure of NH3 squared over the partial pressure of N2 to the first power, the partial pressure of H2 cubed. Okay? And so you would just set it up accordingly. So 5 minus 2x squared over x times 3x cubed. So the way I set it up, the way I picked the problem, this would be hard to solve. But if you had this on an exam, probably, most likely, this would be like some form of a quadratic. And then you probably have to use a quadratic formula if you have a KP problem. I would say, at least half of the time, it'd be a quadratic formula sort of thing. There's usually nothing you can assume it's small, in general. Now, one more nuance about this. Take a look at this line right there. One question we often ask when it's a KP problem is, what's the total pressure at equilibrium? The total pressure is the sum of the E line. So if we ask you that, P total is the partial pressure of NH3 plus partial pressure of H2 plus partial pressure of N2, which is just the bottom line. So in our case, that would be 5 plus 2x would be the total pressure. So once you find x from the equilibrium expression right above, then you can solve for the total pressure if we ask that. But it's a common way for us to pair P total with this ice table sort of question. Okay, so that's Kp. If you need to convert, let's just do one more thing here. Kp equals Kc times RT to the delta n. So that's if you need to convert. Let's zoom out a little bit here. So say if you knew Kc, what would be R? There's two R's, you know. It's the 0.08206, that R, because this is from the ideal gas law. T is in Kelvin. What's delta N for this question? It's only for gases. If there's no gases, there's no change in moles, and this is 2 minus 4. Okay? So that would be negative 2. What happens if delta N is 0? What does that mean? Kp equals Kc. Is that okay? Alright, cool. Next, let's move on from Kp. That's enough of that garbage. Let's see. What else we got? Oh, I kind of did partial pressures. The person who asked that want to say more about that? Oh, Raoult's law. I don't, oh, maybe I can come up. Do you want a practice problem or concept or both? Okay, I'll try my best. Let's say we have a container of A and B. So if there's two items in the container that are liquids, or more, if there's two or more, this is probably a Raoult's law, especially if they're not reacting. Okay? So if they're not reacting, we're probably talking about Raoult's law. They'll have some vapor pressure up above. Okay? Now let's compare this. If we just had A or we just had B. This will also have a vapor pressure up above, and A will also, both will have a vapor pressure up above if they're liquids. Okay, let's look at this one right here, just B. B itself has a special name for this pressure. What's it called? It's called the pure pressure. If it's just B, we call it the pure pressure of B. If it's just A, we call it the pure pressure of A. If it's A and B, you can't do any of that stuff. Okay? This would just be, you could call this P total. Or, if you wanted to, you could say P total is PA plus PB, or the partial pressures. But pure pressure does not come into play when it's not pure. Okay? Hopefully that's somewhat logical. And I cannot add these two numbers to get P total. That's a common mistake students make. You can't add these numbers to get P total. Okay, so we're going to use Raoult's law, which says, for example, for PA, it's XA times PA naught. Or PB is XB times PB naught. So if I wanted P total, I have to add both of these, because the mole fraction changes the pure pressure. Okay, this mole fraction right here refers to what state? This mole fraction refers to what state? Your only two choices are the liquid or the gas. It's the liquid. Both of these refer to the liquid only, not the gas. So when you're finding the mole fraction, it's the moles of liquid that you're talking about. Does that make sense? Not the moles of the gas. We don't care about that. Moles of the gas are associated with Dalton's law. All right. So a sample question. Let's see if I can make something up that might work. Let's say we probably give you PA naught. Let's say it's 550 torr, and let's say PB naught is 100 torr, and let's say you have in the container of A and B, you have 1 mole of A, and let's say you have 3 moles of B. Okay? And I want the partial pressures, and I'll want the total pressure. Pretty common question. So then you would just say, okay, let's find the mole fractions first. Mole fraction of A is the moles of A, 1, divided by the total moles, 1 plus 3, or 0.25. The mole fraction of B equals the mole fraction of B divided by the total moles, 1 plus 3, or 0.75. What do you observe about this, or what do you already know? The sum of the mole fractions better be 1, or you've screwed up completely. Okay? So the sum of those equal 1. Then you just move into the rest of the problem. So the partial pressure of A is the mole fraction of A, like you see on the top, so 0.25, times the pure pressure of A, 50 torr. So your answer will be in torr. Let's see, what is this? 12.5. And the partial pressure of B equals the mole fraction of B times its total. So that'll be 75 torr. And then P total is just the sum of PA plus PB. 12.5 plus 75, which is, what, 87.5 torr? There we go. Any questions about this? It's just that, so make sure you just know how to use the formula. Okay, next. We're rolling. I'm just going fast because I want to make sure we get as much as possible done. Just to say a little bit about vapor pressure, and this will combo with Clausius-Clapeyron, and I think, do I have something about this in my reader? When you see something about vapor pressure, there's multiple places where that could take place. Okay, maybe I'll just have to remember. Let's write the Clausius-Clapeyron first. National log of P2 over P1, delta H, vaporization, divided by R, 1 over T1 minus 1 over T2. Okay, there's a Clausius-Clapeyron. How do you know if you're using this? You know you're using it if you have more than one pressure and more than one temperature in your question. Then it would likely be this. If you have a vapor pressure, and let's just do a little bit of scratch work here. So this problem could use the word vapor pressure, or the phrase vapor pressure. Meaning, instead of saying partial pressure, sometimes you might see vapor pressure. So for example, the vapor pressure of water at 50 degrees is so much. This could be this question if they ask, what's the vapor pressure at another temperature? So for example, well, I'll get to that in a second. Another sort of question, so I'll put this Clausius-Clapeyron, you can see it happen there. You could see the phrase vapor pressure come up when you're using the ideal gas law. Vapor pressure, that would just be the P in the ideal gas law. This is if you have one pressure and one temperature, then use the ideal gas law. If there's more than one pressure and temperature, you're talking about the Clausius-Clapeyron that we just wrote down. You could see vapor pressure in Raoult's law. If you see the phrase vapor pressure in Raoult's law, it's again talking about the pressure on the left-hand side. Okay? So that pressure in particular. This would be not two temperatures and two pressures, but a mixture of more than one compound. So if there's more than one compound and you see vapor pressure, then you're talking about Raoult's law. Okay? So those are the most common calculation places where to see vapor pressure. There might be a couple more, but those are the ones that come to my mind first. Okay, now let's go to a question. Did you want me to do an example? Okay. 10 people want me to do an example. So let's say I want the vapor pressure of water at 50 degrees C. And let's say you can't look that up. I just want to calculate it. Okay. This would actually be a Raoult's law question. And here's why. You should know, theoretically, or by the time you get to the final, that the vapor, at 100 degrees C, that's the boiling point, what's the pressure of water? 1 atm, or atmospheric pressure. So that's something you should know if you don't know already. And then on the back of the exam, you should be able to look delta H of vaporization of water. Okay? I believe, I can't remember for sure, but I think it's 44,100 joules per mole. Okay? So let's use that information. This one's from the back of the final. This other one, you should know that at the boiling point, the pressure is atmospheric pressure. And so now I can solve this question. Even though the second point wasn't given, it just should be locked in your mind as always a potential point. Okay, so you would just say, I want to know the vapor pressure. They want to know P2 is what they want to know. P1 is the 1 atmosphere. And that equals delta H of vaporization, 44,100, if that's the right number, joules per mole. Remember to put this in joules. Sometimes we give it to you in kilojoules. You need to convert to joules. And then divide that by R. Make sure it's this R, the 8.3145 R, not the other R. The other R is only for the ideal gas law. Okay. Then you go 1 over T1. That goes with P1. So 1 over 100 plus 273. Or 373. Then 1 over T2, we're curious about 50 degrees, so 50 plus 273. And solving that should get your answer. I just made it up, so I don't have an answer. What you would want to practice, though, is make sure you can take the anti-natural log of both sides on your calculator and not screw that up. Okay? If you're concerned that you screwed up, look at some old examples, either in a textbook or on our YouTube channel, and make sure you get the same answer. Or if you have some from lecture, redo them and make sure you can get the same answer. This is a common calculation for people to screw up. All right, next. Let's do the bomb calorimeter. Bomb calorimeter, how does that work? That is when you have a calorimeter that's a closed, isolated system, and there's some sort of reaction happening in there. And so the typical setup is the sum of the Q's equals 0, and there's 2 Q's. Oops, equals. There's a Q for the reaction, and there's a Q for the calorimeter. So whenever there's a reaction, there's a Q. So that's how you know the first Q exists. And then whenever something changes temperature, that has its own Q. And usually for a bomb calorimeter, we consider the whole calorimeter to be one entity, and it's all increasing so much temperature. Okay? So you only have 2 terms in the typical bomb calorimeter problem, and typically you want to solve for Q reactions. So let's do that. That'd be minus Q cal. And then that would just be C delta T. So the heat capacity, not the mass times the specific heat, but the heat capacity times delta T. How do you know if it's one of these questions? Obviously, if you see the word bomb in there, it would be one of these. But if they're asking for a Q of reaction, and you see the word calorimeter, it could likely be this. And then if you notice if the heat capacity is given instead of the specific heat, it's likely one of these. So if the heat capacity is given instead of specific heat, again, that's another reason. So they'll say the calorimeter went up by such a temperature, and here's the heat capacity. You would just multiply these 2 numbers to get your answer. There sometimes is an additional step on these. So I'll kind of say, here's the first chunk of the problem. Sometimes it'll stop there. Sometimes there's a second step to this problem. It would go like this. We'll change colors a little bit. We would want to say, for this reaction with a certain amount of reactants. So the most common reaction that we're talking about is a combustion reaction. That's another hint. It could be a bomb calorimeter if you see combustion. And what they want you to do is take your Q reaction answer and divide by the amount they just gave you. So for example, say the amount is 5 grams. You just divide your answer by 5. Whatever amount they give you, and then your answer will be in joules divided by the amount units. So if the amount units is in grams, joules per gram. Amount unit is in moles, joules per mole. Okay? All right, that's all I have on bottom calorimeter. Let's move over to the exam 2 material now. Let's do the common ion stuff first. First, the person or people interested in common ion, did you want the concept? Did you want a calculation? What are we talking about? Yes? Both, of course both. What else is there? Okay. So, for a common ion, this could appear in a couple different scenarios. Okay, it could appear, let's write this down, common ion. You could see a common ion most likely for a buffer problem or for a KSP problem. Okay? It could appear elsewhere, but that's just less naturally likely for this class. So that's what we're talking about. So let's tackle both those areas. KSP is a little easier to look at, so let's start there. First, we'll work on the concept. Let's say you have something like calcium fluoride, okay? And then it's a solid. Let's write its reaction. You should be able to do this. That would be calcium 2 plus aqueous plus 2 fluorine minus. Okay, there's our reaction. You have a KSP for this reaction. Is that large or small? Extremely small. Okay, so you should know that. Is the reactants or products favored? The reactants are favored if K is small, always. K is large, the products are favored. Also should know that. Okay, so here's your typical ice table. We'd ask you for molar solubility, which would be X. And you ignore the solid, and let's say this is 0. Typically say that's 0. Okay, when you start off a normal problem. And so you go plus X here and plus what here? 2X, because that 2 right there. This would be X and 2X. And the way you'd solve this problem typically that's not a common ion, you just say, well, that's X times 2X squared, because there's 2 fluorines. So notice that the 2, this 2 right there, appears here in 2 places in this problem. There and here. Okay, these are the same 2's. Okay? All right, that's your typical problem without the common ion. Now let me get my pen out and say, hey, instead of 0, let's say we gave you 0.15 molar of fluorine. So then you'll have 0.15 molar of that. Not there, but down here at the bottom. 0.15 plus 2X. And then that'll change your KSP. I'll write it in black. X times 0.15 plus 2X squared. That's how the problem would change. It changes by this 0.15 right there. Okay, conceptually first, and we'll talk about the math. Conceptually, when you add a common ion in this kind of problem, what happens to the solubility? Goes up or down? It should go up. Down. So when you add the common ion, sorry, I went crazy, too excited. What happens is you add the common ion, it's going to cause a shift to the left. And it'll make more solid, so it should go down. It should be less soluble. Okay? It should be less soluble when you have a common ion because it's going to shift it to the left. Okay. Oh, we'll get to that. Yeah, we'll do that when we get to the next section. Okay. So it should be less soluble with the common ion. All right. So that's the general concept. You should expect a smaller number from this in black ink than the one in the blue ink. All right. Here's the other thing. When you're solving this, let's get a different color out. Is X here going to be large or small? Okay, let's try it back up a little bit. What's the favorite side? Products or reactants? The reactants are favored. So if reactants are favored, you would expect a very small shift to the right in the C line. That means X is small. X is going to be small when it's going away from the favored side. If the favored side is the left, and you have the plus X on the right, then X will be tiny. And in all these kind of questions that are related to KSP, X should be small. So you're going to drop this term, and it becomes very easy to calculate because you're assuming the x is very tiny. Okay, so that's how you do the math in the second one. In the first one, you have to take a cube root to get your answer. All right. Any questions on the KSP part before we move over to buffers?
Question?
Yeah.
How do you know that KSP is small?
How do you know KSP is small? That's not an assumption. That's just a pure fact in this class. So I don't know who asked that, but I hear your voice. The KSP, we're focused on insoluble compounds in our class. So that means we're focused on things that don't dissolve, meaning they want to stay here. We have not learned the math of things that want to dissolve. So we're focused on small KSPs in our class. Okay? So we're always having KSP small, the reactants favored, and X small. And by small, when K is small, it's smaller than what number? The number 1. Say K is large, it's bigger than the number 1. Okay? And K for KSP problems will be significantly smaller than 1. They'll be like 10 to the minus 4s or 10 to the minus 15. Okay. For buffers, what would that look like? Well, let me write out the possible reaction. Let's say HCN plus water. This is the general reaction for an acid. You should be able to write this, given the acid. This is aqueous, the water is liquid, goes to Cn minus, aqueous plus H3O plus aqueous. Okay, there's our reaction. Typical, now I'm going to do the same thing, ice. We'll typically, in these kind of problems, ask you for pH. That's our favorite thing to do with acids or bases. What's the pH? So what you would do, you ignore liquids or solids, and then we typically give you a molarity here. I'll just put capital M for molarity. We give you that number. This would be 0, and you go minus X, plus X, plus X. So then you go molarity, whatever we gave you, minus X, X and X. And then you would say Ka, because it's an acid, is X squared over M minus X. And these sort of questions for a weak acid, is K large or small? K is small. And so what side is favored? The reactants. So is X large or small? X is also small, so we're going to drop this X right there. Okay, let's do scratch paper, because I don't know if I believe you all. Okay. Small. No, I need more scratch paper. Small. Large. Don't know. Okay, we're going to make a little table here. KSP is small. Ka for what is small? A weak acid. I'll put WA for weak acid. Kb is likewise small for a weak base. Kf is large. Ka for a strong acid is large. Kb for a strong acid is large. Kp, don't know. It could be anything. Another way to say this, it could be anything. Kc could be anything. Did I miss any Ks? Oh, Ka1 for a Ka1 refers to what thing? What concept? Polyprotic. Ka1 for a strong acid is large, so same pattern. Ka2, Ka3 for anything is small. Is that okay? Did I miss any Ks? I can't think of any more right now. Okay, if you don't know that, you should know that right now. Okay? So this is, when I am asking you, hey, is K large or small, this is what's in my mind. Okay? All right. Can I move this? Done? Yes, question. Oh, yes, sorry. I wrote strong acid. Strong base right there. Good, good. Okay, remove this. Let's go back to this problem here. Okay, that's your typical problem. You would solve for x, and then pH is negative log x. Okay, that would be your typical problem. Now let's change that with a different color. We'll do purple. Okay, now in a common ion question, cross out that 0. We're going to have a number here. What number? What letter should we use? I don't know. 0.15. I don't know. I just picked a number. So this would be x plus 0.15 here. Okay. So then for the purple question, the common ion is in purple here. Ka would be x times x plus 0.15 over m minus x. And in this case, you're going to drop both of these x's because they're small again. Okay? So both of those would be small. Oh, okay. We'll go back to that other page in a minute. And then you would solve accordingly. Or, and this is again for the common ion, so I'll keep it in purple. You could realize you have what right now? You have a buffer. You have an acid and its conjugate base, and they both have some molarity. So when you have a buffer, you can skip the ice table, forget all about that, and say this is pKa plus the log of the base over the acid. In our problem, the base was 0.15, and the acid, I didn't pick a number, I just said it's capital M. So, if I can zoom out like this, all this in brown here, where my fingers are, and then the top part of, and then this, you could skip all of that and use the Henderson Hasselbach. It's your choice which one you prefer. So you can do all of that where my fingers are, or you can skip all of this and then use the Henderson Hasselbach. Yes? Acid and conjugate base, that's right, when you can do that. And the molarities are similar within a factor of 10. And then, theoretically, though that doesn't come up too often, the volumes would be relatively large. A couple, like a liter or something. Okay, let me go back to this for a second here. When is x small? Okay. I'll do this in purple. X is small, and I'll put an asterisk. X would be small here, typically here, 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 here. So those 6 scenarios, you would have a small x. Is that okay? So if you didn't know that, there we go. There's more quality stuff for you. You should charge for this. This is so good. Okay. Huh? Yeah? For the KF is a small x for the opposite reason of the other ones. It's large, the products are favored. And so what you're going to do is you need a 0 on the unfavored side, which is the left. That means you're going to plus x backwards towards the reactants, and that has to be small. So I guess you could almost do the same thing with strong acid, strong base, but we never fall into that scenario. So we don't ever have to deal with that for the strong acid, strong bases. But basically, if x is not around 1, if it's large or small, x will be small. So you can see the situation pretty much, x is small. We just don't come into that scenario for strong acids and strong bases for any problem we've ever solved. And of course, if you don't know, x is probably not small here. So if you want to write that down, x is probably not small in these 2 scenarios right here on the right. It's probably annoyingly a reasonable number, and you cannot make any assumption there. Okay, next. Let me just say a little bit about buffers since we're on them. I'll go back here. Okay, let's do the type of buffer problems and then I'll stop with buffer. Number 1. Oh my gosh, how are things going so fast? Okay, number 1, Henderson, Hasselbach, plug, and chug. Okay, so they give you all but one variable, you plug and chug. Okay, number 2, they just want you to find the pH of a buffer. This is again a plug and chug sort of situation. They give you all the numbers. Maybe you have to look up Ka on the back page, but it's plug and chug. And then the third scenario, you add a strong acid or a strong base to a buffer. That's kind of the third common type, and these are only calculation problems. But calculation problems, you add something to a buffer. In this case, something you'd want to remember is you're going to do stoichiometry first, then you're going to do the Henderson Hasselbach. So you're going to do a stoichiometry problem first. You're going to make sure there's a 0 on the unfavored side, and then you're going to go to Henderson Hasselbach. Okay? So if you feel a little fuzzy on that, make sure you definitely look up an example. I just saw the time, and it's flying, of course, because we're talking about chemistry, so we should go on to the rest of the things. Let's do titration curves. Titration curves. Let's do a pH, a strong acid, strong base, pH versus volume. A titration curve for one of these. Would it start off at a high pH or a low pH? Low pH because it starts off with the strong acid. Which one of these, the strong acid or strong base, is the one that's added? The strong base is being added. Which one of these is the one that's the titrant? The strong base. The second one is the titrant. It is being added. That's what titrant means. Okay. So it would look like this. A perfectly symmetrical S curve where this is called the strong acid region, this is called the strong base region, and this is the EQ point, which equals what number? 7 pH. Okay, no calculation necessary for the EQ point there. Now the opposite would be a strong base, strong acid titration. That would be pH versus volume. It would look like that. The exact opposite of the top one here. And so, again, the first is the strong base region, and then the strong acid region. And here's the EQ point, still at 7. Okay, next. Let's do a weak acid, strong base. Does this start off at low or high pH? Well, you start off with weak acid, which would be low pH, meaning lower than 7. Because it would be acidic, but it wouldn't be like 0 or 1. Probably be starting off somewhere around 2. Okay, so you get a little hump, a very long flat region, and then the S curve comes. So this one is not symmetrical. We've got, this is the buffer region first. Here's the EQ point, and then we got the strong base region, and this is the midpoint. Okay. The EQ point is the pH equal to 7, greater than 7, less than 7. Greater than 7. Okay, because you form a weak base, so that causes the pH to go up a little bit. Okay, lastly is the weak base, strong acid titration. It's the kind of inverse of the one. It's reflected through a horizontal line of the top one. So it looks like this. Something like that. Again, the buffer region starts off. We've got the buffer. We've got a midpoint, which is literally midway to the equivalence point. And then we end with the strong acid region. Okay, the EQ point, the pH is greater, less than, or equal to 7. Smaller because you start off with a because you generate a weak acid at that point. Okay, that's titration curves. Whoever asked that. Next, let's do this one. Delta G versus delta G standard. These are two different things. Delta G standard is equal to negative RT ln K. We'll give you that formula. We'll give you this one. This is delta G standard plus RT ln Q. Okay? So, standard typically means at 25 degrees C. This is the one on the right. 25 degrees C, 1 bar, 1 molar, and I think I got everything. 1 molar, 25 degrees C. So that's that one. This comes from tabulated values typically. Okay, so we can usually, if we give you a table, I'll probably show you an example in a minute. You see a table of numbers, we're probably having you calculate delta G standard. This one is anything that's not 25 degrees C, 1 bar and 1 molar, 1 bar, 1 molar. So anything that's not that, which is every other scenario in the universe, okay, then it's this one. So we're talking about something that's not at what we call standard state, which is what the 0 means. You're going to use this equation at the bottom, okay? Do you want to see an example of that? No problem. Okay, let me just flip over to it here. Yes, awesome. Yes, okay. I don't know how you're going to write this down, but here's a typical question. You can take a picture of it if you want. Okay. I'll talk about part A while you figure out how you're going to write this down. The most important is write down the table at the top. Okay? So, for this reaction, see how we give you a table? We're probably going to ask you for delta G standard. Once you see the table, you know that's probably coming. And you know we're probably going to ask you for K. That's probably coming too. Yeah. A K and Q is the same from chapter 14. Capital K is the equilibrium constant, like Kp, Ka, Kf, Ksp, all those. Q is the reaction quotient, which tells you which way something shifts, to the right or left. So you compare Q and K. Shift to the right, plus X, whatever, blah, blah, blah. Okay? All right, so you know those two are coming. Delta G standard and K once you see a table, most likely. And then there's D through G here too. All right, so I need to move this now to start writing stuff down. Okay, what's delta G standard? How do you do that? Part A, delta G standard, that's right, I heard somebody say, is delta H minus T delta S. So you can find delta S and delta H, you can find delta G. Delta H, standard, products minus reactants, because we give you the formation values here. So you're going to go products minus reactants, open brackets, products. So negative 635.1, there's one of those, plus negative 393.5, and there's one of those, minus the reactants, minus 1206.9, and there's one of those. Okay? Close brackets. Okay, delta H, I got 178,300 joules per mole. Or really, I would just put in joules. Okay, so there's delta H. Delta S is going to be the same sort of calculation, but with the S row. So let's try that. Delta S standard is products minus reactants. So products, 38.2, there's one of those, and 213.7, and there's one of those. Close brackets, minus, open brackets, 92.9, one of those. So products minus reactants. For delta S, I got 159 joules per Kelvin. Okay? So now to find delta G, I'm going to use the formula at the very top here. Okay, I'm going to use that right now. So let's get a different color pen. Delta G standard is delta H, 178,300 joules, minus T, oh yeah, that's given in the question here. Right there. So you put 1,000 here. Typically, if it's not given, it would be 25. And 1,000, that's in Celsius. So you gotta add 273 to that. Okay. Times T, that's T delta S, 159 joules per Kelvin. Okay, I gotta move this out of the way. I don't have any space. This is negative 24.1, 24,100, sorry, joules. There's your answer to part A. Part B, at standard state, is this spontaneous? Yes. How did you know that? Yeah. So yes, it's spontaneous. Why? Because it's a negative number. That's what negative delta G means. C. What's part C? What is K? K at 1,000 degrees C. Well, now because we're asking about K, there's only one possible formula. It's this one, minus RT ln K. So delta G is minus 24,100. R, 8.3145. T, 1,000 plus 273, or 1273. Natural log of K. Remember, K is the equilibrium constant. And there's a negative sign. Nice. Okay, so you got to solve for K. You can see if you can try this at home, see if you get the same answer. I got 9.76 for K. That's part C. Part D, what is the equilibrium partial pressure of CO2? That's part, let's see, D? Yeah, D. We want to know for D, what's the partial pressure of CO2? Well, let's write the reaction. Oh, here, I can just give you the reaction. There's the reaction right there. So let's write K, Kp specifically. It's products. What goes in the numerator here? Partial pressure of CO2. Why don't I add CaO? It's a solid. What do I divide this by? Yeah, 1 or nothing, because that's a solid. So what's the answer? 9.76. It's the same. Is that okay? No? Okay, they're the same because that's the equilibrium expression. The gas is the only one you'd include. Okay, what's the answer to what's the question to part D? Oh, I got that. E. What is delta G? And specifically, we're saying, what's delta G? Notice there's no standard here. So this is the other formula for delta G. Let me write that down. Delta G is delta G standard plus RT ln Q. And it gives us the partial pressure of CO2. Partial pressure of CO2 is 10. So we're going to change it from 9.76 to 10. Okay? It definitely can be 9.76 because that's the equilibrium partial pressure. Remember, Q represents partial pressures not at equilibrium, or concentrations not at equilibrium. So delta G we found in part A, that's minus 24,100 plus R, 8.3145, times T, 1,000 plus 273, or 1273. And the natural log of Q, which they gave us in the question, is 10. So you just plug in the numbers, and this turns out to be 270 joules. That's what I got? Yeah, I think that's what I got. 270. Okay, part F. So you can calculate that at home so you get the same answer. Part F. Is this reaction at partial pressure of 10 spontaneous? No, why not? because the delta G is positive. So did you notice that delta G standard can be negative, but delta G can be positive? That's okay. All right? So at not standard state, it's not spontaneous. I think there's another part. Or no? Huh? We'll skip the last part. Yeah. Q is a partial pressure of carbon dioxide. That's right, because it's the only thing that's not a solid in the question, in the reaction. Yes?
For the initial calculation of delta H and delta S,
Yes.
on the table, it says
Did I miss a number?
in the units, per mole, per mole.
Yes.
So you calculated the actual H and delta S for the reaction.
Where did the moles go?
Yeah.
Is that your question? Yeah, there's kind of two takes on that. Where did the moles go? One is, my take is this is, the coefficients are all 1. Specifically, that means moles. 1 mole of this, 1 mole of that, 1 mole of that. So when I multiply by this 1, I'm multiplying by moles. And thus the mole units drop out. Some people, you'll see when they do the calculation, they just leave the moles in there. So it's their preference, but for me it seems like I think the units should cancel because you're multiplying by moles. Yeah. Yes? Oh yeah, make sure, I guess part A asks for kilojoules. So make sure in part A you would have converted this to kilojoules because that was requested you. Was that your, did I get your question? Yeah. Make sure you answer the units they request, if any. Okay, move that to the side. Okay, I have a question for you because you gained a 440. Do you want to do more of this? Do you want to do more of these, or do you want to just pause and go to specific questions? People want to do more of this. Okay, I mean, if you want to leave, I don't care. But yeah, we'll do more of this. This is fast. Let's do W and S. This is probably would be a multiple choice sort of question. K is a constant. W is the number of microstates, and S is entropy. This is a way to find entropy. It's also the definition of entropy. Entropy increases as the number of microstates increase. So the number of possible states of a mixture or of a compound, the more states it could occupy, the higher the entropy. So if it could occupy just one possible state and it's stuck, there's less possible entropy. Entropy kind of represents the randomness, or really the unusable energy. So if it could have 2 states, W is 2, it would have higher entropy. The more states it can occupy, the higher the entropy. That's really the definition of entropy. It's related to the number of states, or technically microstates, that it could occupy. All right, and so for the third law, W would be 1. So the third law says, third law of thermodynamics says a perfect crystal at 0 degrees Kelvin has entropy of 0, or absolute entropy. That means there's 1 microstate. So that's the only item that could possibly have 1 microstate. A pure perfect crystal at 0 Kelvin. Okay, that's really all I have on that. It's more of a conceptual item. All right, next. I have a question for you. All 5 classes are here right now. Any of your classes not cover activity? Which class are you in, if you say no? Wait a minute. People raise their hand and now their hands are gone. Does that mean you're not sure? Any depth? Yeah, not counting lab. Lecture. Who did not cover activity? What class? What class? Yokobayashi? Is there some agreement there? Oh, why did you raise your hand way earlier? Okay, now I'm going to say something else. If you went to all 5 classes, I don't know how it's possible to have a common final. If one instructor says skip titrations, we couldn't have titrations on the final. Is that logical? Okay, can I continue now? That didn't make sense, you got to think about it. Okay, let's do solubility in pH.
But we didn't really do that. Because they're just specific. They're just specific.
Yana, were you like, I know.
All right, here we go. Let's say we have an ionic compound, ionic, okay, a metal and a non-metal, and that dissolves into its aqueous counterparts, its aqueous ions. There are 2 ways, and our question is, how can we increase solubility? How can we increase solubility? Because is K large or small? Small, KSP, remember, is in the small category. This is a KSP. We want to increase solubility, so we want to shift this to the right. We want to dissolve as much as possible. So there's 2 strategies to do so. Strategy 1, if N minus the anion, so if the anion is basic, then add an acid, which would be the same as decreasing the pH. That will, if you add an acid, the acid will react with N minus, removing it. Because the acid is like bases. The acid and base will react, N minus will go away, and this will shift to the right, making it more soluble. Okay, possibility 2. How do you make this more soluble? Possibility 2. If M plus, meaning the cation, is acidic, and typically it'll be a Lewis acid. What do I mean by that? What's a typical Lewis acid? A transition metal, or anything under the staircase. Staircase isn't labeled, but for example, lead, or bismuth, or tin. Those would be Lewis acids. Transition metals or anything under the staircase, if those are Lewis acids, so if you see one of those, it's acidic. Okay? So if you have a transition metal, in other words, you can add a base or increase the pH, and that will remove N minus, that will remove M plus and shift it to the right also. That's your 2 strategies. You attack the cation or you attack the anion. So for what people asked me, this relates to KF. Let's get to KF now. So that's the general thing. Somebody asked me about this, and then somebody asked me about KF. So let's go to KF now and see how that applies to this. Okay, let's get a different color here. There we go. KF. What kind of problems can we have with KF? First kind of question we could have is it's only a KF problem. So KF, or a complex ion, is the only item in solution. Okay, that's the only thing. A complex ion is something with a transition metal in it. So if it's a transition metal in KF, then it would be one of these. And typically you're going to use the ice table to solve. To solve for an equilibrium concentration. Okay? Second type of problem you could have is a KF and a KSP in your question. If you have both of those, okay, maybe I can come up with an example, I'm not sure. Then to solve this, you'll also likely use an ice to solve for the same thing. Either of these could use stoichiometry before ice table. So either of these could involve stoichiometry before you have to start the ice table in your question, okay? All right, so those are the two types of math problems you would typically see. Let me see if I can. Okay, this will kind of take us to the end. Is there one of these you want to see more? Do you want to see them equally? Okay, there's 1, 2, or both. Who wants to see 1? Who wants to see 2? Who wants to see both? Okay, I shouldn't have asked. I should have said, oh, you guys don't want to do it. Okay, let's see. If I can help out. This you can make up your own questions too. They're not too hard to make up. I'm flipping over. We're going to do a type 1 sort of question here. And I just need to flip over to my table of KF values in order to do this. Let's say we had cobalt, hexaamine cobalt 2. So this complex here, aqueous. And I said I start with 0.1 molar cobalt 2 plus and 1.0 molar, ooh, is that what I want? What do you think? Think about it. Yes, yes. Okay, ammonia. Okay, I want the equilibrium concentrations. We see that you want the equilibrium concentration. It has to be an ice table. Write out the reaction first. So write out this reaction. Here it looks the opposite of a KSP, where you write the individuals first that are aqueous, but in this case the product is also aqueous for any KF sort of problem. Okay, so there we go. You would generate what you think is the ice table. I'm not going to write the whole thing out yet. And then we'll say, okay, this is 0.1. Oh. 0.1. And let's say this is 1.0. Okay? And this is 0. I can't continue my ice table yet. Does anybody know why? I need a 0 on the unfavored side. So let's think about this. Is KF large or small? Small. It's large. It was the forward reaction wants to happen. The products are favored. So if KF is large, I have a 0 on the favored side. I don't know how your other instructors explain this, but I need a 0 on the unfavored side, which is the reactants. Okay? So the unfavored side obviously the opposite of the favored side. So I need to do stoichiometry first. So I'm going to subtract off, because it's so favored it wants to go forward. What do I subtract off here? Yeah, 6 times 0.1. So this 6 right here appears here for the first of 3 times. So it's going to appear here 3 times because we have a stoichiometry here. And I'm going to add 0.1 over here. 0.1, I'll have 0.4 and 0. Now see how the 0 is on the left side, the unfavored side? That, what I just did is called stoichiometry. This now is the true eye line. Okay? Then now I can start my ice table. It doesn't have to be that you do stoichiometry in one of these problems, but it's common. Okay, so I'm going to go plus x, what am I going to do here? Plus 6x plus minus x over here. Minus x. So it'd be x, 0.4 plus 6x, and 0.1 minus x. Okay. That 6 from up there is also here. That's the second of 3 times that's going to appear in this problem. Okay. It has to appear there for stoichiometry reasons. Now, let's write out the KF. KF, which I can look up, or on the exam you'd be given, is 4.5. Wow, it's a kind of a big number. 4.5 times 10 to the 33rd. Cool. So it's big, as you can see. That's products, 0.1 minus x, and then x, and 0.4 plus 6x. What else do I need here? This is to the 6th power. Okay, so that 6 right there is the third of 3 times. That 6 right here is the third of 3 times that the 6 appears. All right, what am I going to do next? Assume x is small. Lose that one and lose that one. And now it gets really easy to solve. Remember when I put those asterisks on that table earlier? Here's another example where x is small, because kf is large. Okay, so now you can solve this at home. I don't have the answer because I just made it up, but it's this is the setup, 0.4 to the 6th power. Okay? Yeah. Yeah, mathematically the other x cannot cancel out, or you'd have 1 over infinity. Oh, is there another x? That the x doesn't cancel? Because you're only canceling x when you're comparing it to something, which means it's an addition or a subtraction issue. So if you give a millionaire a penny, you've given them nothing. The x you've given them is small. But when it's multiplied, if you multiply a millionaire's money by 1%, that's a big deal. So multiplication or division mathematically is significant. Okay? That's the shortest I can explain it right now. Okay, so that's that. Let's see if I have a KSP problem. Oh, yes. Yeah. Let me see if I think I have a hope, but little hope. Let's see if I can come up with something. Oh yeah. Okay. This will be the last thing I'm going to do. Okay, this could be a problem where we ask you for molar solubility, and you would do an ice table right now if you wanted to do molar solubility. We're not going to do that because you didn't ask me KSP questions. But if I want to increase the solubility, because I have a transition metal, in the question you can see a second compound. If you see a second compound, in addition to a solid, and we talk about solubility, it's one of these kind of questions right here. So let's say I said, okay, to this, we're going to add, I need KSP first. KSP for this question is 4, wow, small number, 4 times 10 to the minus 38. Okay, so let's say in this question I added cyanide. So I'm going to add cyanide to this, a certain amount, okay? What you would find, we would give you the KF value for this, and it turns out there's this compound that it'll form, an iron cyanide with 6 cyanides on it, and it has a 3- charge. Okay? So when you add cyanide, this compound forms. So you can see that the cyanide reacts with the iron and takes it away. If this is taken away, the reaction is going to shift which way, right or left? Yeah, as you remove this, it shifts to the right. So it's becoming more soluble right now. This is a way to make it more soluble. Well, you can write the reaction. Say, well, aqueous, 6 of these, and an iron. Okay, so there's our reaction. Given this product, you should be able to write that reaction. This is related now to KF. Oops, orange. Leave that. This is KSP up here. This is KF down there. Okay. So what you would do in this question, I'll just kind of set it up for you. These irons cancel, and you'd add these two reactions. You'd add those two reactions right there. And typically what would be given is this number right there. And yeah, typically the cyanide, what I just underlined, is the number that would be given in the question. Okay? So if you wanted equilibrium concentrations, right here you would do an ice table. You would write that number down, you ignore solid, and you're like plus 3x plus x. And you kind of go through and solve your ice table accordingly. So that would be an alternate. This would be the second type of question that was related to KI. Okay? I don't think I have time to fully solve it now, but hopefully at least a setup can get you somewhere. All right, are we good for now? Good luck, study for the final. I will stay around and answer some questions about specific questions.